The N64 has a very distinct but famous art style that seemingly more and more games are trying to emulate. I find it to be a very charming aesthetic, and the low polygon count and low resolutions have an almost dreamlike feeling that leaves a lot to the imagination. The N64's aesthetics were not only defined by limitations, but also by some choices and oversights that were made back in the day. The most significant factors of this aesthetic are its low polygon count, the blurry textures, the simple lighting effects, and the way animated characters have these interlocking fat rolls for limbs. Now, there are very good reasons for some of these, but not all 4 of these aspects have to be present on the N64. I've been programming for the N64 for 4 years now, and I will explain how limitations affected this art style and how some techniques were overlooked that could have been used to get around some of these art style limitations. All of these require ingenious solutions and insane knowledge about the inner workings of the hardware, so it shouldn't come as a surprise to anyone that these were not implemented at the time or only later during the N64's lifespan. And the blurry textures were mostly caused by the lack of cache space available for textures. The texture cache of this console was only 4 kilobytes in size, meaning the biggest texture you could load into it were 64 by 64 250 step grayscale textures, 32 by 64 full color textures, or 64 by 64 textures with only 16 colors, or even 128 by 64 16-step grayscale textures, but I've never seen that last one being used in any official game ever. I'm guessing the low step count just looks too weird in-game to actually use this one. While that was a high resolution back then, by modern standards, this gave the N64 the trademark blurry texture aesthetic. And to be honest, I don't think having a higher resolution would really have helped anything, considering most games on the console rendered in 240p. But there's one option that was underused here. The N64 is capable of holding 2 different textures loaded at the same time, and it's also capable of even just using one texture twice at different sizes to make the tiling less obvious. Mario 64 only used this technique a single time, on the Bowser painting right here, and it didn't use it to increase resolution, but rather for this cool blending effect. This opens up the possibility of using one texture as a detail texture and another as a contrast texture, or any other combination you like to do. This technique is basically mandatory to make big fields look good, and Nintendo also used it whenever they had a grass plane in games like Ocarina of Time or Majora's Mask. If you look closely, you can see that there's one big grass color texture here and one repeatedly tiling detail texture. You would think that using 2 textures is more expensive, and I assume that is why they often avoided using it. But once you actually benchmark the numbers, you find that this can actually be cheaper than using one texture and is often the same cost due to a hardware quirk. How can that be? Normally, the console renders triangles in 1 cycle mode, but using 2 textures requires the 2 cycle mode. 1 cycle and 2 cycle mode are different in ways that I'm not even sure I understand correctly, but Tharo and Wiseguy have independently benchmarked both 1 cycle and 2 cycle mode speed, and they found that 2 cycle mode is about 5% faster when the drawing depth test never fails and the triangle is always in front, and at most 30% slower when the depth test always fails and is hidden behind another triangle. Meaning, if you have a material that renders at least 83% of the time in front, this technique is faster or equal to 1 cycle. This is often used in the mod I am working on to both save performance and look better, and has become a pretty popular technique in the modding community. It looks awesome on emulators, though admittedly it makes less of a difference on real console. Not sure if I'd call this an oversight, considering it was used, but it's definitely underused and should have been taken much bigger advantage of. Just goes to show you that you should always benchmark your processes before you try to make any statements about optimization. I think they could easily get high enough resolutions out of textures using this method to not actually need a bigger cache. That's right, I am disagreeing with what everyone says sucked about the N64. I think the texture cache was big enough actually. crucify me. Another workaround here is also dividing a texture into multiple parts, which also is very expensive. James Lambert has a pretty cool demo that does this at runtime to render a scene with HD textures on real hardware. This is obviously very expensive to render and it takes a lot of storage space. So this is pretty unreasonable to use on actual games. But you can use this to a lesser degree on logos around the world. Most N64 games also use a technique like this to render backgrounds. Mario 64 specifically uses the 248 by 248 texture, split up 64 times for its backgrounds. Although it is scaled so big that it still looks super blurry. Another significant part of the Nintendo 64's art style was the low polygon count. Polygons are being calculated by a dedicated hardware part called the RSP. The RSP would receive a microcode from the game that it is running, which it would then use to compute triangle data and figure out how to display triangles on the screen. For games with early microcodes like Mario 64 or games with less efficient microcodes like Diddy Kong Racing, this makes sense. The RSP in these games is pretty busy calculating all these triangles. But almost every N64 game ran on the much better F3DX or F3DX2. And if you profile them, you'll find out that the RSP actually only needs a few milliseconds to compute all these triangles. In the scene here, you can see it takes only 8 milliseconds despite the scene having 3000 triangles. Realistically, you can probably get away with 10,000 triangles in the camera view on the N64, as I've showcased before in a dedicated video about why polygon count is not as important as most people think. To render a game in 60 FPS, you need to finish in 16.7 milliseconds. And if you look at super low poly games like Mario Party, it probably only ever renders 1500 triangles at most. So unless those games had something horrific going on under the hood, their polygon budget was a lot higher, and even though low poly Mario is charming, they absolutely could have gotten away with just using Mario 64's model. Though keep in mind, even with the RSP finishing in just a few milliseconds, it doesn't mean it's free. The N64 has a shared memory architecture, meaning the CPU and GPU all share the same memory transfer speed. The RSP is going to use a lot of memory transfers to send all the triangle data between memory and RSP, meaning it will slow down other parts of the N64's architecture, like the CPU and the render output. For this reason, I think this is a bit of a blurry line between oversight and not an oversight. I think low poly was way overemphasized back in the N64's day, but there were benefits to going low poly for almost all the games. It's always cheaper, easier and safer development cost-wise to just cut the triangle budget in half and not worry about having to squeeze every bit of performance out of the machine. When we talk about the visual charm of the N64, one element often overlooked, yet pivotal, is the lighting. In the realm of modern gaming engines, we are spoiled with reflections, occlusions and sophisticated light play. But the N64, with its more modest capabilities, had to approach lighting differently. The N64 was not nearly strong enough to do those computations. Also, all the available microcodes on the N64 have almost all their effects work per vertex instead of per pixel, meaning the vertices had to hold the entire render state and colors could only be interpolated between these vertices. Most commonly, the game would just store a light source with a light color and then multiply the vertices color with how much it is facing the light. You can see this easily in Mario 64. The camera is the light source, and you can pretty easily see how everything gets brighter when the light source is shining at it, and goes darker when the light is facing away. Some games took this a little further and pre-generated the light, stored it into vertex colors, or even used triangular shadow cutouts to fake real shadows. While the light looks pretty cool in this scene from a mod here, this was all stuff that was done back in the N64 days, especially in Rareware and Factor 5 games. The new F3DX3 Sauron is working on these days adds a few cool new things, such as cell shading and ambient occlusion. Though these were not easily available and probably not even invented yet at the time of the N64, so let's not count those as oversights. But there was one super cool feature, or maybe even bug, the N64 had that you could use to get some beautiful light effects that were never used as far as I can tell. Usually, colors of a texture are multiplied with a light source's color to output the final color. This is one disadvantage. It looks like there's no reflectiveness to the materials, and this becomes very apparent if you watch out for it. Even stuff like the metal cap just had a whitish texture with no actual reflections going on. But there is a way around this. The N64 uses a color combiner instead of a shader, where artists can input a math equation that calculates a pixel's color. So for example, we can multiply a texture with our shade color here to get a nicely shaded sphere, or we could even multiply it with a flat primitive color to get an unshaded sphere. And this combiner came with a cool quirk. If a color channel grew bigger than 255, but output a value lower than 384, the console would clamp the output back to 255, so channels would slowly max out. You can achieve this by doing some additive combining in the color combiner. For example, look at the shade multiplied by texture 0 plus primitive combiner here. As I increase the primitive color, the sphere slowly caps out on color values and it looks like it has a reflective spot. People like Gameplay have been using this quirk to get some awesome lighting effects. By abusing the clamping, you get some cool overexposure effects and the materials will actually look reflective. For this reason, the N64 was capable of much more impressive lighting effects than we'd usually see, though you do need to be clever with it to actually make it look any good. The overlap between math skills and art skills required to effectively take advantage of this is so huge, so I imagine this was just too difficult to work with or to figure out back then. But the biggest tragedy of it all was what happened to animated characters' limb connections. The people developing the first N64 microcode, Fast3D, had a cool technique built in that I don't think was used at all for games released in the first 3 years of the N64's life. And this technique would have gotten rid of the iconic fat rolls on the characters. Let's talk about why they exist in the first place. Transforming vertices one by one, like in modern games, is very expensive. Most games opted not to do that and just supplied a display list plus transformation matrix per body part on the RSP. A transformation matrix is basically just a 4x4 table of numbers that you can multiply with a vertex coordinate to get a new position. It can easily hold information such as scale, translation, and rotation. The transformation matrix will be calculated from where the animation bones were, so they simplified animations into just computing a handful of bones instead of hundreds of vertices. The command chain for this looked like this. We load our matrix, and then we load our vertices in, and whenever the N64 loads in the vertices, they are instantly being multiplied by the last transformation matrix. And then we draw a triangle connecting our pre-multiplied vertices. This has a drawback. Any limb is not going to know where the previous limb ended. So for example, an elbow is not going to know where the upper arm vertices are, and it can't connect to them. All it knows is where to render and with what transformation. This means they had to make closed-off limbs like that to avoid visual holes in between limbs, which adds a bunch of polygons and it looks a little odd. But the developers of the microcode and hardware have built a way around this that is entirely free of cost and would have prevented this oddity, while also lowering the amount of polygons the game has to render. To use this, we can take advantage of the fact that vertices are transformed on load by the current matrix supplied. That means if we lay out our comments like this, we load the matrix, we load the vertices, we load another matrix, and then we load a few more vertices, and then we draw triangles connecting the old vertices to our new vertices. Now we can use the vertices transformed by a previous matrix in our drawing, which in the case of an elbow would be the upper arm, and connect the mesh without any holes. I've manually added Mario 64 to do this to connect Mario's limb in a hex editor a long time ago, and this saved 124 out of Mario's 760 polygons while removing the gaps between the limbs. Yes, I did it in a hex editor. I 3D modeled in a frickin' hex editor. Look at it. Can you see anything? What the fuck was I thinking back then? Unfortunately, it seems most games completely overlook this capability, leading to the look we're all familiar with. It's especially unfortunate because it lets you get away with less polygons too. And doing this in Super Mario 64 with its fast 3D microcode is actually super difficult, because the early microcode that Mario 64 had only allowed you to keep 16 vertices loaded at a time, meaning you could only connect a maximum of 15 of them to the previous limbs. But in later microcodes, such as F3DX, you'd get 32 vertices, making this much easier. And even better yet, with Sauron's modern F3DX3, we can even use 56 vertices, allowing for even more complex skinnings. Nowadays, we can use this technique really easily with Fast64, and almost everyone working on mods uses it now. By just connecting the limbs, the tool will automatically set up the rig correctly for you, and it will work. No more Hexador 3D modeling. The children are playing, and the birds are cheeping. Life isn't so bad. It's not implemented perfectly yet though, but it works well enough. If anyone's willing to use Python and offer their free time on perfecting this, come join the Fast64 Discord and help them out. We're still missing some features to avoid repeat vertex loads, which would make this technique even more efficient than it already is. In conclusion, if we were still developing games for the N64 nowadays, most of these characteristics making the N64 era's art style so distinct probably would have slowly disappeared over time. But they certainly have a charm to them. I'm going to try to get the best looking game out of my mod, so even though it is an N64 game, its textures will look less blurry, the poly counts will be higher, rigs will be connected, and there will be a few lighting effects, and I hope you don't mind. And I also hope you enjoyed this video and that I will see you in the next video. Big shout out to all my Patreons for supporting me on my journey. Without you guys, I would have stopped making videos a while ago. If you want to appear in the Patreon credits, make sure to check out my Patreon. I really appreciate the support.